In this video, I'm going to highlight some key points in Experiment 11, which was the last practical that you did in Term 3 August this year. This Experiment 11 is the exact question from 2017, last year's A-Level Practical Exam Paper 4. Okay, and because some classes were unable to complete the debrief, therefore I'm doing this video. Okay, now before I begin on Experiment 11 debrief, just to run through this part very quickly. The difference, let's compare, because in kinetics, there are two types of experiments. Initial rates versus continuous method. What is the key difference? Initial rates is referring to many different experiments, usually at least 4 or 5, or even more. Experiment 11, however, continuous method, such as Experiment 11, there is only one experiment carried out. Okay? So, we follow the concentration usually of one substance. It could be a reactant or product throughout the entire reaction. That is continuous method. Whereas for initial rates, we do many different experiments. You are very familiar with this. We have done this in our PJC prelim this year, paper 4. You carry out 4 or more experiments. Each time you vary the concentration of one reactant specifically, and you keep the other concentrations of other reactants constant, and you find out the effect on the rate. If the concentration of that particular reactant doubles, the rest of the concentration is constant of other reactants, and the rate doubles, we know it's first order with respect to that reactant. Okay? And you also know that there are two types. Rate is proportional 1 over T for color product, and the other type rate is proportional V, color reactant over time, the color reactant one. Okay, so now let's focus on continuous method, which is Experiment 11. So just to refresh your memory, okay, in this experiment, we are interested in investigating the kinetics of the decomposition of hydrogen peroxide. Hydrogen peroxide decomposes to give us water and oxygen gas. And what you will be doing is the titrometric method, which means that you carry out a titration during a continuous method, okay, to determine the concentration of something. Okay, in this case, you are going to titrate the peroxide at different times throughout the reaction, okay, in the reaction mixture with manganate. So let's take a look at what is happening here. Okay, just to summarize, what is happening here is simply that you prepare 100 cm³ of Fa2, your hydrogen peroxide, into a conical flask and label it reaction mixture. Okay, in step 2, you can see over here reaction mixture. And at the point when you add 2 cm³ of iron 3+, that is your catalyst. Once you add it in, you start a stopwatch and swirl to ensure that it's a homogeneously mixed solution. And after that, what do? You take a measuring cylinder, you measure out 50 cm³ of sulfuric acid of this concentration into a second conical flask that I've drawn in purple. And let's say at time is equal to 2.2 minutes, you transfer a 10 cm³ aliquot of the reaction mixture into a 10 cm³ measuring cylinder using a dropping pipette, which is none other than a dropper. And after you have transferred 10 cm³ of reaction mixture into this measuring cylinder, you transfer it into this second conical flask, okay, with the acid, and swirl. And the moment you add in this 10 cm³ aliquot to the acid, you will record the time to the nearest second. Okay, the purpose of this acid is really to quench the reaction. So you can safely assume that once you pour in at, let's say, T is equal to 2.2 minutes, the reaction will have stopped at 2.2 minutes. Okay, and then you can go on to analyze what is the concentration of hydrogen peroxide in this reaction mixture at 2.2 minutes by titrating it with manganate, because we know that hydrogen peroxide reacts with manganate in this mole ratio. So this is what I have meant earlier. Okay, after you transfer 10 cm³ of aliquot of the reaction mixture at 2.2 minutes. Okay, then you introduce acid. You then take the second conical flask that you have the reaction mixture at 2.2 minutes with the sulfuric acid. Quench already, right? Okay, then you titrate with manganate. Then you record the volume of the manganate that you use. Take note, this should be FA1. Okay, I also want to point out something that it's important to read whatever question you are given carefully, because at the start, when they told you to prepare and titrate the reaction mixture, you can only carry out once, because it is after all a continuous method where you do the experiment only once. And secondly, you have to transfer your first aliquot, the 10 cm cube, within the first 3 minutes of starting the reaction. Okay? And you should not spend more than 25 minutes maximum on this experiment. Okay, we have actually warned you many times that you do not spend so much time doing the experiment. Collect the data, move on. Okay, because the time is needed for you to complete the entire analysis, calculations, and so on. If not, you know that 3 marks are deducted if any part is left blank. Please do not leave any blanks. Now let's look at the graph. Okay, basically, this graph over here, I want to explain that the y-axis is volume of Fa1 manganate in cm cube. Please label the units against time TD in minutes. Okay, how to make sense of this graph? Basically, what we really want is actually the concentration of peroxide versus time. Do you agree? Because after all, the kinetics of the reaction we are really interested in is the decomposition of peroxide, whereby peroxide is my only reactant. Therefore, the rate equation will look like this. Rate is equal to K times concentration of my reactant peroxide to the power of A, the order of reaction with respect to peroxide. But it is not, okay, I would say that it's actually proportional, because the amount of peroxide is proportional to the amount of manganate. Therefore, from equation 1, please go and look at your equation 1 at the very first part, the top part of this worksheet. The number of moles of peroxide over number of moles of manganate is 5 over 2, right? So the number of moles of peroxide is 5 over 2 times number of moles of manganate. And, okay, and the number of moles of peroxide is 5 over 2. If I split up the amount, number of moles of manganate is actually, M is C times V, right? Concentration times volume. And because my concentration of this manganate is constant, because the stock solution, I'm always using the same concentration of manganate. So I can prove that the number of moles of this peroxide is K times this. That means directly proportional already. So the greater the volume of manganate, the more peroxide I have in that 10 cm cube aliquot, which makes sense. The more manganate I need to titrate with the solution, the more peroxide there is in that solution. Okay? So this graph of volume of KMnO4 versus time is as good as peroxide concentration versus time, simply because of this relationship, because the volume of manganate is proportional to the number of moles of peroxide. Okay, and if you are thinking, but concentration of peroxide, this is not concentration, but the concentration of peroxide is actually just, in the reaction mixture, is just the number of moles of this peroxide in the titration divided by the volume. But the volume each time is actually 10 cm cube. It's a constant. Okay? So that's why the volume of manganate is proportional to the concentration of peroxide in the reaction mixture.